Today we're going to be discussing Nikola Tesla's dynamic balancing machine. This is the patent drawing, and what we see here very briefly, this is a lathe mechanism. So you have a X and Y movement. There's a grinding wheel on top. The rotor is in this casing that is cut open here, so you see the rotor sticking out a tiny bit. These are his two bearings. This is the balance indicator and a speed indicator. This was just used here to heat the air coming in. The air is used to spin up the rotor to a speed that is relative to the critical or resonant speed of the rotor. And that is all described in the patent. Here we see a little close-up of the balance indicator. And it's just a ball bearing with a needle and a little weight to adjust the sensitivity. And at the bottom, this is the side view. So you see how the rotor is in line with the center, or the rotor is in line with the center of the grinding wheel. And that's where it's ground off. The air enters here. The rotor spins this direction. The grinding wheel spins in the same direction, and that's how it's graded off. And I built my own little version of this system for my miniature rotors. So we have a slide table for the X and the Y, for precise X and Y movements, a Dremel 3000 as the motor, and a little grinding wheel on there, 38mm grinding wheel. Then we have a stand for, this is now one of the miniature rotors that's on there, and you see the balance indicator over here. It has a tiny bearing in it and some weight that are these nuts. I might have to tweak this a little because sometimes it starts flying all around. So, but we'll see how that goes. And there's an air flow coming in from this air gun over here, this duster. So that comes out to this, I don't know if you can see it, all this black on black, but it's a converging nozzle. So the air hits it at the bottom. The rotor will spin in this direction. The grinding wheel will spin in the same direction, and then I can use this wheel to move it past the rotor to balance it. But before we do that, we're gonna have to make some initial measurements. So the rotor we really want to balance is in here still. And so I'm going to be measuring what the top speed is using this meter to see how fast can we spin it without balancing, and then use this little app here on the phone to measure the vibration, just to see how unbalanced it is. And then we'll balance the rotor using my little machine, and we'll see what the difference is, if we can get it to a higher speed then, and if there's less vibration. So let's get to it. So here is the data from the run. We see there were a few resonant points. For now, these values don't say much yet. They're only going to be valuable once we can compare them to the run after the balancing. And since we reached about 502 Hertz, if we multiply that by 60, we get around 30,000 RPM on this little unbalanced rotor over there. We're going to try to balance it, see if we can improve it. In the balancing patent, Tesla mentions that the bearings should be yieldably mounted. So that's what I did here. You can see the orange bit. That is Ninja Flex material. So that's a flexible 3D printed material, and you can see it gives the rotor the ability to move a little. Then it mentions that the grinding should be affected at a speed that is related to the critical speed. The critical speed is the resonant frequency really of this of the rotor. Here's the rotor, and to determine the critical speed, to calculate it, we need to know the weight of this rotor. So I have a microgram scale here, or at least a precision scale. And let's see, we first put the whole thing on. Hope it stays. Come on. There we go. 17.46. And then I'll put just a shaft on, identical shaft. 5.42. So now we can calculate 17.46 minus 5.42 equals, so the rotor itself weighs about 12 grams. Okay, I want to focus a little bit on something very important that not many people understand. And this is, we're looking at the balancing patent again from Tesla, and he says the speed at which the grinding is affected should bear a definite relation to the critical corresponding to the fundamental natural vibration, and the following rules should be observed. If the system is run in two bearings, like our system is, the grinding speed should be an odd multiple or submultiple of the critical. I think a lot of people read this and think, sure, whatever, but what is the critical and why does Tesla think it's so important? So the critical speed, like in his old machines, you know, his Tesla coils, everything was about resonance. Well, that's what he's talking about now as well, the fundamental natural vibration of the rotor on the shaft. That's what he's aiming for, because there the vibrations are strongest, and that's the best place to balance the rotor at. So what is the critical? Let me show you some more museum documents about that. So we have this one in which Tesla says, I highlighted it here, if the operation is performed at a speed below the critical speed, static and dynamic balance is simultaneously affected. If above the critical, then only dynamic balance can result. In the first case, material is taken off from the heavier side, and in the second from the lighter side. So this tells you that what you want to do is balance at a speed below the critical speed, because then you'll both statically and dynamically balance your rotor at the same time. So again, in this patent it says we're going to be needing an odd submultiple of the critical speed. So how do we calculate this? Well, there's another document in which Tesla, this is called rotor construction. He describes here a crazy 60-inch diameter turbine, and he mentions here that actually he's working backwards. So he says, like, I want the critical speed to be around 6,000 RPM. What diameter of shaft do I need for that? So if you go, I went through all these calculations trying to figure out what he was doing, trying to see if it matched, if the formulas he used correspond to any formulas that are being used today for balancing, and somehow it just didn't see all these inputs here. They just didn't really match up with an existing formula. So I was a bit lost, to be honest. Like, here's some more of the math, and he comes down to that he would need a 6.56 inch shaft to have a critical speed of 6,000. Well, because I was stuck here, I was looking online to see, okay, how do we calculate the critical speed of a shaft? And what I found was this website that was super helpful. And you see there's like a bit of the theory explained, and then it also shows the formulas for several types of shafts. So this one is a cantilever, so one is sticking out. Here we have one with a central mass between two bearings, if the mass is like slightly offset. So there's all kinds of formulas. And so what we're going to be using is the central rotating mass for short bearings. There's not really a definition of what a short of a long bearing is, but I believe this is what we're dealing with. So I took this formula over here and I implemented this into a little spreadsheet. And this, actually what we're looking at now, is the input that Tesla shows in the museum document. And I filled in all the, so for example here, the total rotor weight ends up being 2,200 pounds. And if we look at what Tesla says here, is that over here you see the total weight is 2,212 pounds of the whole rotor. He takes the end disc, the inside disc, the spacers and everything together. 2,212 pounds. That's also what's in my spreadsheet. Then we have the 6.56 inches shaft diameter over here. Sorry. So we have that as well as an input. The length of the shaft, that was somewhere else. And then the Young's modulus, which has to do with the elasticity of the material. Well, he is using steel, so I got the Young's modulus for that. And yeah, what that ends up giving me is a critical speed of 6,059 RPM, which is the 6,000 RPM that Tesla was mentioning and targeting in his document. So that seems to coincide. Now what's really funny here is down here he says if he wants to lower the critical to 5,000, he can reduce the diameter of the shaft to 6 inch, and that should bring the critical down to 5,000. So let's see if that happens in our calculator as well. So if I set this to 6 inch, we see now we have 5,000 RPM critical speed. So this calculator works, even though it uses the more modern version of the formula. This is the exact same, so it comes from the same source that Tesla was using, and that's this article actually. It's in Van Nostrand's Engineering magazine by Rankine, I don't know what his last name is, how it's pronounced, but this is sort of the source of all these balancing formulas. And so even though Tesla arranged his a bit differently, we come out to the exact same results. So yeah, that's how I verified that my calculator works. And so then I made a couple of copies, but this one is actually about my small rotor that I'm trying to balance. So we have the 12.02 grams, the shaft diameter 3.175 millimeters, which is 1/8 inch, and the length of the shaft between the center of the bearings. And we have the Young's modulus, which is very low because it's made out of carbon fiber reinforced PETG. This is the one value in my case that I'm not entirely sure about, because this value differs greatly per carbon fiber PETG filament. And yeah, for the exact filament I'm using, this value wasn't available. I asked the manufacturer, so I sort of had to guess this. But anyways, we see a critical speed of 10,000 RPM, and but what we're interested in for the balancing part is the submultiples. So remember from the patent, because we're in two bearings, we need an odd submultiple. So the first one we encounter is the third submultiple. That would be 3,400 RPM. But because I'm using a multimeter to measure the speed, it shows up in hertz. So what we're actually looking for on the multimeter is 57 hertz. So that is just some explanation. I will make this calculator available in the description, just like the bill of materials for my whole balancing setup, as well as the 3D models for the balancing stand and the Dremel holder. So yeah, let's keep this 57 Hertz in mind, and let's start balancing this rotor. Okay, now that we know the critical speed and that the third subharmonic is around 57 Hertz for us, I'm gonna mount the motor, or the rotor, sorry, in the balancing machine. So here you see the parts. So you have these flexible bearing holders with miniature bearings in it. These are the spacers to keep the rotor centered. Of course, the balance indicator, and these bolt down to hold the bearings in place. So let's go. So the rotor is now mounted, and the first step is actually written down here. Preliminary to the application of the process, we have to run the part at a very low speed to true it with the wheel. That's to make it concentric. And so how we're going to do that? We're going to take this marker, color in the whole edge, and then I'll slowly run it against the grinding wheel until it's concentric. Okay, the whole edge is colored in. That will allow us to see if we've grinded off all parts of the rotor, something off all parts of the rotor. So you know it's concentric. So I can't spin it with air to a low enough speed and then grind it, because this rotor is so light it has no inertia. So I'm gonna have to turn it by hand, but I don't want to have my finger too close to there. So instead I'm gonna attach this coupler to the shaft here so that I can actually spin it from that end. Okay, time to balance, or at least time to true. So I'll turn this on. Okay, so now the rotor, there's no more red visible on the edge, so that means the rotor is now concentric. So that is the end of step one. Okay, let's have a look at the balance indicator before we actually start balancing. So remember, we only made the rotor concentric so far. To be honest, I'm a little shocked at how little the balance indicator moves. It seems like this rotor is not that out of balance actually, or this indicator is just not working as it's supposed to. But anyways, let's try the balance and see if we can get it to be even better. Okay, I'm ready to start balancing. Remember, we are targeting around 57 Hertz, as that is the third submultiple of this rotor setup, and that's what Tesla recommends, to use an odd submultiple for setup with two bearings. So let's give it a go, see how it goes. Okay. Well, you saw that at some points the RPM was going down when the rotor hit, or the grinding wheel hit it. So I was really trying to balance between, not scraping off too much at one go, because then the rotor would slow down significantly. So I was trying to keep it, a bit above 40 hertz. But yeah, it is quite fickle and tricky with these tiny rotors. So I think this would be a lot easier if your rotor is a bit heavier. But it seems like it's pretty, I did find some heavier spots where the RPM or the hertz went down more than in other places. And I think I've managed to scrape some of those parts off. So I want to do one more run to see how the balance indicator is reacting now. Okay, wow, that does seem to be a big difference. The balance indicator now really hardly moves. It almost stays exactly in the middle line. So it seems like it did something. So I'm gonna place this rotor back in its casing, run see if we can reach a higher RPM now that it's maybe balanced, and also see what the vibration app tells us. Okay, the moment of truth. Last time with an unbalanced rotor we reached about 503 hertz as a top speed, which was around 30,000 hertz RPM. Sorry. We're also going to measure vibration again, so we're going to see the effect of balancing a rotor. So I'll start this vibration measurement and let's go. Okay, that was a new top speed, 523 I believe, so 523 times 60 is 31,380 RPM. So it's an improvement for sure. I was hoping for more of a difference, but anyways, we're gonna have a look at the vibration as well to see if we can see anything improving there. So we're looking at the results from the vibration measurements with the phone. So on the left we have the unbalanced run, which was before the balancing, and then on the right the balanced run after the balancing. What you see when you look at the resonances, we see that after the balancing, several resonances have disappeared, and the ones that remain are either lower or the same as they were. So and in the graph as well, you clearly see visually that there are no real strong resonant points anymore, even though in the one on the left you see clear peaks in several places where there was a significant point of resonance. So it does definitely seem that the balancing has done something to improve the performance of the rotor. So yeah, I think we can call this a mild success, and I'll definitely keep trying to improve it further. So after recording the videos, it turns out I made a mistake. I used the Young's modulus of the rotor material, which is carbon fiber reinforced PETG, but actually I should have used the Young's modulus of the shaft material, which is steel. So this is what I used in the video, but actually it should have been this. Huge difference. So we went from a critical speed of 10,000 to 60,000 RPM, which makes a lot more sense to me because I already thought it was quite low. So yeah, we were using the third submultiple, which was 57, as you can see. So we were using the third submultiple, but so I was a bit worried, like, have I been balancing at the wrong point now? But actually, if you go down, you see the 17th submultiple, 59, which is very close to 57. And also, if you watch the video, you see that that's where I'm at a lot of the times, balancing at around that speed. So I was still using an odd submultiple, but it was not the third one, but the 17th one. And the thing is, the closer you get to the critical speed, the more strongly the shaft will start whirling, and so the better you can balance. So ideally what you would do is you would start out low, for example the 17th, and then work your way up to 15th, 13th, 11th, and as high as you can get. That will give you the very best balance. So this could explain why my balancing did something, but not like as much as I hoped. Maybe it was because the rotor was not that unbalanced to begin with, but it could also be that I just had to work my way up this ladder a bit further. However, with my current wimpy air gun, I can probably not get any further than about this point, because without a case, I can't get it to spin much faster than this, unfortunately. But anyways, that's just a little bit of an update on an error I found, and something to keep in mind. That's why I said shaft Young's modulus now. And yeah, this machine that I built works for rotors between 1 to 2 inch in width and or in diameter, I'm sorry, and then up to 30 millimeters, so that's about, let's say, slightly more than 1 inch width. So yeah, if you want to give this a try, check out the links in the description, because there you can find all the 3D models. I'm giving that stuff all away for free. And also bill of materials, if you want to buy some of these parts, like the slide table or the grinding disc for the Dremel. And yeah, also the calculator, of course, for the critical speed, which is, I think, something that that's very going to be very helpful for people, as there's not much information about that. So thanks for watching this extremely long video. I didn't plan it to be this long, but we had a lot to cover. So I hope you learned a thing or two, and if there's anything wrong, if I did anything stupid, please let me know, and I'll be happy to answer your questions in the comments. Talk to you later.